In the previous hour, we introduced Prestack migration. So let me repeat it. First of all, in terms of implementation, Prestack migration has three elements. One is a downward continuation. You downward continuate the source wave field and the receiver wave field separately. Right. The second element is the implementation or the calculation of wave equation. So how to generate the downward continuated wave field. Third element is the image condition. This image condition is different from a Prestack migration. In the Prestack migration, the image condition has a physical meaning, but here it's the image condition simply is a cross correlation. Okay, so as I said, this is one of the research direction for some of you when they come out the new image condition instead of a cross correlation. You come out a new image condition can generate the true reflection coefficient. That would be revolutionary for the industry, right? But I do not see this yet, based on my limited reading. That's the Prestack migration. The procedure actually for Prestack migration is almost straightforward after the introduction, right? Of course, because the data in the Prestack domain is huge, and we do a migration point by point. Typically, for the wave equation-based migration, we do need to do the whole data sets together. We cannot do the target area only. So time is consuming, right? Really linear proportional to the time samples, data samples in the original data. Now, because the migration is based on the step-by-step downward continuation, so migration itself, in principle, is a depth migration, right? And the downward continuation along the depth direction. Although we see in the Prestack migration, we see the final result is displayed in the time domain, but the implementation for migration itself is in depth. So let's focus on the depth migration. We saw this PowerPoint before. Because we have an angle, we have a dipping angle of refractor. So the stack section is not the image of subsurface, right? And the refraction in your stack section is not the reflector of subsurface. So stack section, you cannot treat as a model. You should treat it as a data. And then you do migration, you generate the model, right? We learned this, the solution for this, to remove this effect, to move this sample, migrate the sample to the right position, which is perpendicular, the ray path perpendicular to the reflector. That's called a migration. And that was for the simple, straightforward model, but subsurface Earth model is more complicated than we assumed. For example, you have an anomaly, velocity anomaly here, either high or low. But your wave path banded is not straightforward to the subsurface. However, here the ray arrive to the interface should be perpendicular. So because the curve right here, this actually point is shifted, right? So this effect also should be considered. So that the lateral velocity variations should be also considered, right? And because of this velocity variations, the hyperbolic curve is no longer right. So you have a non-hyperbolic diffractions. Non-hyperbolic diffraction, okay? Actually, I mentioned that we cannot, in the Prestack migration, we cannot use a diffraction stack. That's actually the reason here, right? And also we have a so-called refraction. We will see later. When you use a refraction, which means turning away, you have a much better imaging. We will show this diagram later, okay? So the solution, because of a complication, so we need a post-stack migration, right? In the post-stack migration, what we need to do, first of all, we need a stack section. We need a stack section. Stack sections means after an MO, you correct your seismic trace to mimic a zero offset acquisition. To mimic a zero acquisition, right? And in the migration, one of the key elements is downward continuation in depths. Remember, in depths, okay? And this is called a wave acquisition method. If we do the ray tracing for Kirchhoff migration, this ray tracing, when the ray cross an interface, the instant angle and the reflection angle or transmission angle, they follow a row. It's called a Snail's row, right? Actually, I said in the one of the previous sessions that the ray path, following the ray path, the ray parameter is always a constant. Ray parameter is the cosine theta divided by V. Cosine theta divided by V. So angle cosine divided by V. That's always a constant for a single ray. Doesn't matter how complicated the ray path is. It's always constant. Okay, this is the theory for when we do the radon transform. If we record that, the problem for post-stack migration, we do need to obtain zero offset data, but sometimes even you do the NM correction, if we have for example, if you have two reflectors together, you may make one zero phase, another one zero offset, another one's not, right? So this actually complicated. Okay, and the problem is for an MO, you assume subsurface reflection follows a hyperbolic curve, follows hyperbolic equation, but sometimes you have a move out which is not hyperbolic, right? And the diffraction is not hyperbolic. So if we use a hyperbolic curve to do the correction, you end up errors, right? And we actually also know that it's not easy to move out correction, typically for offset slightly larger, right? NMO in theory actually only works for the very narrow offset, right? But if for single dipping event, that's another thing. I didn't spend time here, but I just mentioned the terminology called DMO, dipping move out correction. So that means we do not only do the flat layer, but we also concede dipping angle, right? But this only applicable to a single dipping layer. But subsurface, actually, you can see the model of subsurface structure is much more complicated than that. So this is why I ignore that, because we straightforward go to a Prestack migration, right? That's cover everything. One more thing, for migration, we need a velocity, right? That's why we do need a velocity. So actual subsurface structure has this problem. So the problem here are the problems. So velocity variation, dipping angle, stacking is not necessarily generate what we want, zero offset data, zero offset trace, right? And the mobile is not harmonic. So all this is sensitive to the velocity model, or sensitive to the velocity model. So if we consider velocity model with horizontal velocity variation and dipping angle, basically you treat this part of velocity different, and that means you effectively have an interface in your model, right? So this problem, the solution for that is Prestack depth migration, Prestack depth migration, right? So what we do one shot by one shot, or one receiver by one receiver gather, shot gather or receiver gather, one by one, or come offset profile or come offset cube. You do one by one, and then finally you sum up all the energy together, right? Follows the superposition principle, right? That's superposition is based on the linearity and the time invariance. That's two assumptions, right? Okay. The velocity analysis, as we said, for migration, we do need the velocity, right? But if we do the Prestack migration, we can use the post-stack migration velocity, which is an MO velocity, tune a little bit to do this as a starting model for migration, and then during the migration processing, we can generate some gather, right? We'll call that common imaging gather for the single image point for all the offset that suppose have a flat reflection. Based on this, we can do the velocity analysis. So Prestack migration, we do iteratively, and then in between, we can upgrade the velocity model, right? Now, let me repeat, for NMO stacking and the migration, you can see the logic. Based on NMO, you generate the velocity, and based on NMO correction, you generate a stack section, and based on NMO velocity, you do the migration, right? That's the conventional way. But for the Prestack, you somehow get a velocity model, you do the Prestack migration, and then in between generate some gathers, and based on the behavior of a gather, try to flatten that, try to update your velocity, and then you redo the migration. And update velocity, redo migration, iterative. You can do it that way, okay? So you cannot simply give a velocity and do the migration, that's one go, no. Just in the iteration. For Prestack migration methods, we already discussed there are two types of methods. One is integral method. One is integral method. Integral method basically is Kirchhoff migration. If we recall that, Kirchhoff migration has some elements there, usually we ignore it. But for the true amplitude, we do need to consider there are two elements. One is the incident angle, cosine theta. Another one is geometrical spreading factor, which is 1 over r squared. So it's not only travel time alone, but during the ray tracing, you also find the angle, you also find the travel distance, right? So you can include these two into consideration. That means you can end up so-called true amplitude Prestack migration based on the Kirchhoff migration. For wave equation method. Again, for wave equation method, we based on the downward continuation. In the Prestack, because it's zero offset, we just do the single downward continuation, right? Step by step. But now in the Prestack, we should do the source wave field, receiver wave field downward continuation one by one, separately. Finally, we do the cross correlation for individual sample, XZ sample. Right? For individual sample, we have a time series, and then we do the cross correlation of 2 time series, and then we take zero lag, which is t equals 0. Just t is not travel time t, that's a lag, cross correlation lag, okay? So the physical meaning is different. There's no physical meaning, in fact, just zero lag. But in the Prestack migration, t equals 0 does have a physical meaning, which means you assume your refractor is an exploding surface. Your source, each individual point of a refractor is a so-called source. And why I emphasize that, because in the Prestack migration velocity, where you do not use the true velocity, use half the velocity. Velocity divided by 2. If you recall that, because your wave field from surface downward gradually towards the reflector. So that's only one way, right? But your sourcing data is 2-way. Your source propagating down from source, wave start from source point, propagating down to the reflector and come back to the receiver. So 2-way. But the migration here only is 1-way, right? Because your surface gradually downward continued to the reflector. So that's why in the migration, you use not use the velocity itself, use half the velocity, because it's only halfway. Okay, so this difference. And in terms of migration methods, in terms of the numerical method to solve the wave equation, you can use finite difference or explicitly. Not many people use FAK method. I think most likely they use a TX method or FK method, FX method, TX, FX, but not many use FK. Because in the Prestack migration, the velocity model is so complicated, we cannot assume, at least for the horizontal direction, we cannot assume velocity is constant, right? For Prestack locally, you can assume that, but for Prestack, we consider all the sorts of complication there, all sorts of complexity. We cannot simply assume this flat horizontally constant. That's the difference. That's why we do not use FK method. So let's see control migration for the depth migration. What we do the trace by trace, or start from sample by sample. But in fact, after all the samples over one trace, we just finish one trace, right? We do migration trace by trace. So it doesn't matter how many traces, we just do one by one. That's straightforward. And for each individual trace after migration in your model space, that sample will be spread to the whole model space, right? So that you need to keep the model space, whole model space. And then finally, well, every time you generate image together, you just stack to that, right? So this is just sum all the images, sum all impulse responses. That's the final result. This method can extend to velocity variation. In fact, it's very, very flexible in terms of complexity of the velocity model. because it's based on ray tracing. However, ray tracing does have a difficulty for very complicated model. There are two things. One, the numerical stability. Two, how to select the ray path you want, because sometimes you have multiple ray paths. Same travel time, but multiple ray paths. We will see later. Normally, we assume a single arrival, a single ray path. Because this method can do applied to any combination of data, because this is better to do the trace by trace, right? So you can do any type of data together. You can use, any type of data maybe you don't know much. For example, you can, for the surface seismic data, you can use shot gather, receiver gather, or comma offset. But just because this only you do one trace by one trace, right? Doesn't matter. It's in which gather. But another implication here, I said, combination of different data. What we learned so far, we have a source in the surface, receiver also on the surface. However, sometimes you also have receiver put vertically in the borehole. This is so-called vertical seismic profiling, vertical seismic profiling method called VSP, right? So use the Kirchhoff migration, you can do the migration for the surface reflection data and the VSP data simultaneously. So-called simultaneously, just the final image, right? But you do migrations trace by trace. Okay, you can do that. And in the migration, the offset information can be preserved. That's important. Why we need offset information? There are two things. Right? One, we want adjusting the velocity. After migration, suppose for single reflector from different offset, they should be at the same horizontal flat because they're from the same depths, right? So depths should be same. Vertical axis depths, so image point should be same. That means if velocity right or model right, you should have a flat reflection in your image gather. But if not, you have curved, you should adjust the velocity, right? That's one thing. Okay, that's important. So you keep the offset information. Secondly, it's important because although those reflections from the same depths, but they're from different receivers, right? Different offset. So amplitude variation versus offset is a key information for reservoir prediction. It's a key information for next step, geophysical application, right? That's the key information you can do number of ways. You can, based on the amplitude variation, to directly predict it's a shale, gas, or water, right, or oil, so-called AVO analysis, or you do a more sophisticated method like immersion, based on the amplitude variation, variation with offset. You do immersion. You can extract a lot of physical parameters, elastic parameters, even later for the reservoir parameters like porosity, permeability, so on and so forth. So it's a very important information for us. So this is why I highlight here in red, amplitude variation with offset. Okay, that's only talking amplitude, but in fact it's not only amplitude, but others, for example, the frequency content also varies with offset, because you travel the path different. Maybe one path just going across reservoir, right? They have a strong attenuation. Okay, so frequency content different. Okay. Also, if we have a same like a lithology but different fluids, you can have a phase different. In the same flat layer, the phase is not always the same. You have in your gather, you can see the polarity changes. If some together, they probably cancel each other. But if you see them in the offset domain, you see the phase different. This also gives you indication different fluids. All right, that's the information very important for reservoir characterization, reservoir prediction. So my major is in the reservoir geophysics, and all my job actually really rely on this information, right? So that's why I emphasize this, right? That's the seismic data linkage to the geology, to the petroleum geology, to the reservoir geology. Okay. Okay. The advantage of a Kirchhoff migration, you can do the portion by portion target migration for the particular gather, for particular horizon, and for particular area. So in that way, you can refine portion of your imaging, refine your portion of. Also, you can save some cost, right? So you do not need to do everything for each iteration. You just do part by part. That's the advantage. Let's show you Traveltime profile, Traveltime imaging here. So you can see the green curves, green lines here, green curves. They are actually the interfaces. Right? So for the Kirchhoff migration or Prestack migration actually involves geological interpretation, right? You have the layers, and this color display here, in fact, shows the travel time. Your source here, your travel time contours here, right? That's the travel time. Okay, gradually move out. So the red means longer travel time. Blue one here is a small travel time. Okay, it's a dot point. It's a source point. Right, that's the travel time. Just a source point. All receive point same, just based on the reciprocal principle. Source from travel time because there's no direction, right? So that's the Traveltime map. So based on the Traveltime map, you do the Kirchhoff migration. That's one of the migration result, a bigger sort body here. That's Kirchhoff depth migration. Vertical axis depth, horizontal axis are just a distance. And there's a sort body you can see. Because Kirchhoff migration can do all sorts of ray paths, you can imaging this sort of body typically in the left and right hand side. That's in a very good shape, right? That's the Kirchhoff migration. However, web question migration, we'll discuss later, it's more complicated, seems, but the result actually is not as good as Kirchhoff migration in this case. Okay, now for web question migration, we use a double square root equation, right? And downward continuate with the depths. Using pre-stack image condition, that's different from post-stack. Pre-stack image condition is correlation. Right? Post-stack is exploding interface, different. Both mathematically see t equal to 0, but it's not same. And for web question method, you should apply to a short record, right? Short record, just so like I demonstrated, you have a short record, but you treat this short record as a so-called source. You propagating from receivers downwards. Meanwhile, you should generate a receiver wave field from source wave field. If these two are the same, have high correlation coefficient, If not, right, you just have no imaging. Okay, so this you can apply to the short record, but also you can work on the receiver short record the same. And but this method losses information of source receive offset. For each individual point, you just take the sample, take the travel time, take the time record at that point, but there's no offset information. Okay, so you do need somehow to find another way to do that. See, common image together. So Prestack verification method does not give you straightforward information for the AVU, right? That's actually currently another research direction, how to generate the image together from verification based migration, right? In fact, just right at this week, last week actually, one of my postdocs just get a paper accepted by a geophysics journal, work on this field, how to generate short common image together from a verification method. Okay, the verification method detail is different, but the same principle here. That's the second research direction. Okay, so you guys know it's third year, fourth year, so you have a long way to do. Even in the geophysics field, there's so many things we haven't solved. At least for my generation, we haven't done that. Okay. This method is a global method. So every time you want to redo that, or you want to do the iteration, you need to do all the data same time. You cannot do that portion by portion. So that's very time consuming. If we somehow can come up idea to do the local imaging or target imaging, that'd be another advantage, right? Because it's a global method, it's very expensive. Verification result is look like this. You can see the sort body here is totally different from Kirchhoff migration. Generally, of course, like a horizontal this interfaces, all good, but the sort body is not good. Do you know why? We use a verification. Verification means we use some calculation follows physical principle, right? But why the results are not so good? Any guess? Any idea? I mentioned that in last week. Okay, when we do the downward continuation, we use the fourth order derivative, but verification is a second order derivative verification, right? What we did? We tried to manipulate the second order verification into the fourth order verification solution, right? So we call it one-way verification. Because one-way verification, so you only see the wave propagating from surface downwards. You do not see any wave from bottom up. So this is why you do not see clearly the boundary of the sort body. So this is limited by one-way verification. Okay. So Prestack migration conventionally we use a one-way verification. And today we also talking about how to use a two-way verification. We will do that. When we use two-way verification, we will somehow overcome this problem. So you can compare this one, you see that difference. But for this part, they were okay, but the sort body image is not right. Now let's talk about migration methods, because I said the advantage and disadvantage for two methods. Typically for the verification method, we haven't exploit all the advantages. Why? Because we use a one-way equation. So here actually we're introduced something called two-way equations, right? So let's review the migration methods. In terms of migration methods, we can, based on the different aspects, we can categorize or classify into different types. First of all, based on the processing procedure, we can divide the migration method as a post-stack migration and the pre-stack migration, right? So pre-stack migration means in this is migration, one step includes stack and migration and all other processing in between. But the pre-stack migration just do one go. Okay. So post-stack migration basically is a migration for zero offset section. So if it's non-zero offset, the semicircle becomes elliptical curve, right? Elliptic curve. So that means it's different post-stack, pre-stack. And in terms of output, if your velocity, you have a confidence to the velocity, confident to your model, you should, the migration method is in depth, should be depth migration, right? But typically for post-stack migration, your model is a smooth model and the structure is not accurate. You very likely output as time. And in the time migration, you assume your velocity variation is smooth. That means your rate path also smooth, right? Okay. And usually the velocity variation laterally is not so strong. Maybe locally it's constant. And the curve, in terms of time migration, you assume it's hyperbolic. Maybe it's not exactly hyperbolic, right? And even you can use a higher order move out, not only second order, hyperbolic second order, right? You have square, but you can have a fourth order or even higher order. And in fact, there also another thing, an Sigsbee effect for higher order involved. For Kirchhoff, that's for two types. And for the migration method, you also have two types. One is the integral method, basically called Kirchhoff migration. Another one is a very equation-based method. Okay, so that's two types. And for Kirchhoff migration, you use ray tracing. And but for ray tracing, you have difficulty when you have a very complicated subsurface model. Okay, velocity variation. Typically, you have like a strong velocity contrast, like solid body or fault, right? And the wave equation method also have a difficulty because when wave equation method, we do downward continuous step by step. So that means you assume the dipping angle is not that high. So if for the steep dipping, wave equation method, downward continuous method, we also have trouble, right? Because we use a one-way wave equation. If we're steep dipping, your wave propagating down actually maybe never come back. So this is why one-way wave equation doesn't work. You need a two-way wave equations, right? You need a two-way wave equation. Let's show you the example. Show you examples here. That's pre-stack migration in depth, two-dimensional. You can see the chalk layer, very strong velocity. That's typical North Sea seismic profile. If one stage you will work on the North Sea data, at this level, just have a strong velocity chalk layer. That's a depth migration. And at a 2D, that's 3D, the difference here. Let's see what's the main difference. For 3D, you can see this structure come up. 2D node, right? So you ignore the structure in the y direction. You only consider x and z direction, right? And this detailed subsurface structure in the 2D, you don't see that. Inside of the chalk layer, you do see much detailed layer structure on the top of the chalk layer, right? Detail means if we have a lateral discontinuity, okay? But in the 2D, this one maybe not necessarily be the true, right? For example, this one looks like a over migrated, but this one could be from the side effect from y direction, right? So after, if we talk about 3D migration, this one is different, maybe differently. Okay. There's a fault here, small fault, and before in the 2D migration. Well, you can, if you see the 3D migration result, you can see there's a fault, right? But it's not as clear as 3D migration. Okay, you can see this very clear. There's fault here, at the bottom of a choke. Yeah, that's the difference between 2D, 3D, and between the depths and the time migration, the same profile. Post-stack migration also in 3D, you have this layer, but you can hardly to do the interpretation for faults, right? For faults, but after you use pre-stack depth migration, you can see the structure here, like faults here, right? You can do the better geological interpretation. The reason is when we do the time migration, we assume the velocity variation is small. We usually, practically, we smooth the velocity model before we do time migration. Right? For depth migration, basically, it's the image of what you want to see. You do the geological interpretation. You know, okay, there's a fault based on maybe based on well log information or based on draining information. Right? You know exactly here there's a fault, and then you can incorporate this information into the migration model. So you can here. So this is a model-based. Migration is model-based. You can see the advantage of depth migration. This example is a synthetic example. Here is Kirchhoff post-stack time migration. Sorry, not post-stack, pre-stack. PSTM means pre-stack, right? K means Kirchhoff migration, Kirchhoff pre-stack time migration. Because time migration, you know, everything's, the structure seems smooth, right? Looks like this. Because it's time, you know, this structure here is not same as the velocity model, right? Let's see the depth migration. You can see here, much clearer. Right, and this salt body and the layered structure underneath the salt body in the depth migration, see much clearer layered structure, right? In the time, because the velocity inference of salt body, the flat layer becomes curved, right? And even here becomes curved, but in the depths, that's more geological sense. You can see the flat, right? Just so you can see that depth migration here, time migration here. So time migration does not give you the straightforward subsurface geological model. Depth it will do. Right. When we do the imaging like a sort body here. We saw the image, right? And Kirchhoff migration has done good job, better job than wave equation, because sometimes we can use this wave hooking downward, here going back upwards. That's called a turning wave. Turning wave, okay? So that means the image can do anything beyond 90 degree. 90 degree means vertical structure. You're right, but here is beyond 90 degree. So you can image this better, right? And the turning wave equation can do phase shift or even Kirchhoff migration, right? But I will use another thing called reverse time migration, which will be the two-way wave equation. So Prestack depth migration result for this structure here. If we use Kirchhoff migration, we have this result. If we use turning wave, you can see, if we do turning wave, you can see the very clear boundary of the salt body. Let me just compare the two. Right? All other parts are identical. That's, you can do not have any significant changes, but the salt body here, you can see the ray, turning ray. This is 90 degree, almost 90, or here beyond the 90 degree. You can see this boundary clearly. So this ray. Kirchhoff migration is flexible, depends on your ray tracing. Depends on your ray tracing, right? If we can do the ray tracing that way, that's good. Now compare the Kirchhoff migration to the wave equation methods. So Kirchhoff migration can handle any velocity variation and any steep dipping event, dipping layer, right? So this is because based on your ray tracing method. But ray tracing sometimes break down because it's too complicated. So you need to improve your ray tracing algorithm. It's nothing to do with the migration, right? We can separate this responsibility, right? So if result is not good, you should go back to refine your ray tracing algorithm, not the migration. As long as you give a good migration, travel time information, you can do a good migration. Most time, assume a single array path. We will show you example if it's not single, why we do need to consider multiple array paths. For the wave equation method, we already said this wave equation for the steep dipping will actually sometimes failed because we use a one-way wave equation, right? Because with a one-way wave equation, we cannot handle steep dipping, right? I show you example here, compares the Kirchhoff migration and the wave equation, both in the Prestack depth domain. So that's the good result for Kirchhoff migration. You can see the salt body image is very good, right? And here, the image is not as good as the depth migration. That's because here we only consider the single layer path. We do not consider multiple layer passes. For the all these small dots here, small anomaly for wave equation, depth migration is also good, right? Let's see the example here. I just try to emphasize we do need improve the imaging by using multiple layer passes. For example, the red pass through here, the black one, and the blue one, they may arrive this point with the same travel time, but the red passes are different, right? One from go this way, one go that way. Okay. In your migration, for Kirchhoff migration, you should consider both red passes, if we can. That means, let's go back to this diagram. That means you can improve the image here, right? I said this not the image here is not good. That's because you only use a single ray pass, and actually you maybe use a ray pass on the right hand side, sometimes left hand side, right hand side. Maybe it's not even systematically use a single ray pass, right? Now, in fact, if it's a single ray pass, you have a Kirchhoff migration look like this. But if it's a wave equation, you can see here it's very complicated. You have a ray pass from here, ray pass from there. Maybe you have somewhere from in between, at least more than one ray passes, right? You can see here. But in your Kirchhoff migration, you only pick up those green curve, right? You didn't get this one. You didn't get the rest one. So that's why your imaging underneath the salt body is not so good. Okay, so the solution for this is called reverse time migration. That's the solution. What is a reverse time migration? Means, well, that's different from a downward continuation. We do not use downward continuation, right? And we simultaneously broadcasting the data back to the Earth, which means we use from source point, we broadcasting data, we propagating data to the subsurface, and the receive point, we also receive data, we also propagating back to the subsurface. The reverse means in the receive part, your travel time starts from the largest travel time and gradually reduced. So time is reversed. In the wave equation, you simply put the wave travel time becomes a minus t. Instead of t, you just change the symbol, minus t, right? So reverse time equation really means you only emphasize the receiver wave field propagation. It is wave equation method. In fact, it's a two-way wave equation. That's the difference from the previous slides when we're talking about the wave equation method, right? That's different, two-way wave equation. In the previous slides, when we're talking about depth migration, wave equation based, it's a single wave equation with one wave equation, but here's two wave equation. That's the very important thing, right? Because we use a proper wave equation, two wave equation, that means we can include all other elements we usually treat as a noise in the previous processing, like a multiples. Right? If we see this one, here it's not necessarily single wave, right? There could be local multiples. Okay, so we include everything. Of course, because with the two-wave equation, because we threw away the downward continuation principle, but we use same image condition, right? We also still use a cross correlation as image condition. This is very expensive compared to the one-wave equation. One-wave equation you can even speed up, use a Fourier transform. So you can use the FK method, FX method, right? Not only finally divisible FX method, right? But for this one, much more expensive. Okay, we'll see detail after the break for reverse time migration.